And I'm going to talk about Lab 4, about oscillations. So our main goals of the experiment was to compare the predicted computed motion with the actual observed motion of a mass attached to a spring, and to then plot the energy changes that occur in the system for the predicted motion. The results were that the computed predicted motion and the observed motion were similar in the x and y axis, and that the total change in energy equals 0. So the first key concept we're going to talk about is Newton's second law, its momentum principle, and how we can derive from there the velocity update formula as well as the position update formula. The second key concept we're going to talk about is the energy principle. In this experiment, the total change in energy within the system equals 0. The system is defined when dealing with changes in energy, and when there is a system with multiple objects interacting upon it, there are different energies acting upon the system. The main energies presented are kinetic energy, gravitational potential energy, and the spring potential energy. So for this experiment, the system is consisted by the Earth, the spring, and the mass of the object. Since everything is considered a system, then there is no surroundings. Therefore, the work done by the surroundings equals 0 as well as Q. We can see also the free body diagram of static equilibrium position for the spring force pointing upward and the gravity pointing downward. Also, you can see that the total change in energy equals 0 and is consisted by kinetic energy, potential energy, and spring potential energy, as well as the net force equals 0 as well. This is the video tracker analysis of the mass attached to a spring oscillating. As you can see on the right, there's the data that we're going to analyze furthermore. The data that we extracted from the video analysis we just saw was that the mass of the object was 0.403 kilograms. We have the time interval as well as the initial position and the initial velocity in vector form. So those same variables I just described were used as the initial conditions for our computational model analysis. We can see the mass of the ball, the initial position, the initial velocity, and delta t. So also, we needed to calculate the spring constant and the relaxed length of the spring. This was done after watching the pre-lecture videos for this week, which explain how to do this in detail. As well, we use some formulas, as you can see, to find the spring constant and the relaxed length of a spring L, and the results are there in the computational model. Also, for a computational model, we needed to find the distance from the relaxed length of the spring, and here's the formula we used and how we implemented it into our computational model. Also, for our computational model, we see that we have involved kinetic energy, spring potential energy, gravitational potential energy, and then the total change in energy is 0. Additionally, we need to calculate and implement our net force and our velocity and position update formulas. As you can see on the top, we have our our formulas we use and how we implemented them below on our computational model. We applied the momentum principle. We calculated the net force by first calculating the F graph and F spring as well. So here you can see the main iteration of our computational model. First, we defined our initial energies. We then calculated the gravitational force, as well as the spring force and the net force as well. And then we applied the momentum principle to update the object's velocity and its position as well. Then we updated the spring constants as well, and then we calculated the energy changes in the system. Okay, and then we use that information to compare the video analysis measurements to the computational model to predict our result. So after we run the program, we get this as a result. As you can see, there's the mass of the mass of the object oscillating, moving back and forth, creating an oscillation. And here you can see our graphical results. On the left, we have the change in energy versus time. In the middle, we have the position versus time graph for our computational model. And on the right, we have our y position versus time, which is for our tracker video analysis. So here we can see some observations I did with the graphs and the computational model analysis. And some potential source of error was that I did not account for other sources, for example, drag force. And I also didn't account for other energies like thermal energy and rotational kinetic energy. And I did not consistently mark the center of mass of the object during the tracker video analysis. So first question, is the energy principle satisfied? So the answer is yes, because by using the changing energy versus time graph, the sum of the change in kinetic energy plus the change in gravitational potential energy plus the change in the spring potential energy equals 0, which is basically what this changing the energy principle says. by measuring the time difference between the x and position data and the y position data, and finding the average period, the average oscillation period for the x position and y position can be determined. The average oscillation period in the x position data is 1.646 seconds, while the oscillation period in the y position data is 1.489 seconds. This difference in oscillation period has a major impact on the calculation for the spring constant K, the spring force, and the spring potential energy. The difference could be caused by drag forces or errors from the tracker analysis.